So, what if I told you there's a new kind of computer coming? One that doesn't just improve on what we have, but operates on a completely different set of physical laws. We are talking about quantum computing. And this isn't about just making a faster chip, no. This is about building a machine that can solve problems we genuinely thought were impossible.
To really get why this is such a giant leap, we've got to look at the basic building block. For decades, our entire digital world has been built on this simple bit. It's just a switch, right? It's either on or off, a 0 or a 1. But the quantum bit, or qubit, well, this is where things get really weird. A qubit can be a 0, it can be a 1, or, and get this, because this is the part that changes everything, it can be both at the same time.
I mean, that simple on or off switch has built the entire modern world, from your smartphone to the internet. But it has a hard limit. When we face truly massive complex problems, like trying to design a new life-saving drug by simulating a single molecule, or cracking the encryption that protects all our data, our current computers just hit a wall. They would literally need billions of years to crunch those numbers.
So, how do qubits get around this problem? Well, they operate using a whole new toolkit of what you could call quantum superpowers. And these aren't just clever programming tricks, they're fundamental principles of physics that let these machines compute in a way that's completely alien to anything we use today.
Okay, first up is superposition. The best way to think about it is like a spinning coin. While it's spinning in the air, it's not heads and it's not tails, right? It's kind of a mix of both possibilities at once. That's a qubit in superposition. And here's why that matters. By holding all these potential values at the same time, a quantum computer can explore millions of possible pathways in a single step.
Next up, we have entanglement, which Einstein famously called spooky action at a distance. So, imagine you have two of those spinning coins, but they're linked. The moment the first one lands on heads, you know, instantly, that the other one, even if it's on the other side of the galaxy, is going to land on tails. This bizarre connection lets qubits work together as a powerful, coordinated team. And the final superpower is interference. Okay, so if superposition creates millions of possibilities, how does the computer ever find the right one? Well, interference acts kind of like noise-canceling headphones for a computation. It cleverly amplifies the signals that are pointing to the correct answer, while at the same time canceling out all the signals that lead to the wrong ones. It's how the computer zeroes in on the solution from a sea of possibilities. So, you've got superposition creating all the possibilities, entanglement linking them together, and then interference finding the signal in the noise. When you put all three of them together, you don't just get a faster computer. You get a machine that completely changes the rules of the game.
And this right here, this is the most important thing to understand. It's really tempting to think of a quantum computer as just a faster computer. It's not. It is a fundamentally different tool, built to solve a very special class of problems, the kind of problems that are literally impossible for any classical computer to solve, no matter how powerful we make it.
Let's take Grover's algorithm, for example. It's the ultimate needle-in-a-haystack solver. Imagine trying to find one name in a phone book with, say, a billion entries that aren't in alphabetical order. A normal computer has to check every single name, one by one. But a quantum computer, using superposition, can look at a huge number of them at the same time, finding that one name exponentially faster. And this is where that disruptive power really becomes clear. Years ago, a mathematician named Peter Shor developed an algorithm that showed a quantum computer could factor huge numbers with ease. Now, why is that a big deal? Because the entire security of our digital world, we're talking your online banking, your private messages, everything, it relies on the fact that this is an impossibly hard problem for any normal computer. So, if this technology is so powerful, why isn't it everywhere? Well, because actually building one of these machines is one of the greatest scientific and engineering challenges of our time. It's incredibly hard. Right now, there isn't one single recipe for building a quantum computer. It's this global race, and you have teams taking wildly different approaches. Some are using these tiny superconducting circuits that have to be chilled to temperatures colder than deep space. Others are literally trapping individual atoms in place with lasers. We're all still figuring out which of these paths, if any, will lead to a truly powerful, scalable machine. But every single one of these approaches, no matter how different, faces the exact same relentless enemy: noise.
This loss of quantum information has a name. It's called decoherence. It's the moment a qubit loses its superpowers.
Its superposition collapses, its entanglement breaks, and it just becomes a plain old bit again, which ruins the entire calculation. Figuring out how to protect these qubits from all the noise and how to correct for errors, that is the single biggest challenge holding this entire field back. But look, despite these massive hurdles, the progress is undeniable. And the reason scientists and engineers are so driven to solve these problems is because of what's waiting on the other side. So, what would a world with quantum computers actually look like? Well, in medicine, for the first time ever, we could perfectly simulate the complex molecules that make up diseases and medicines. This would let us design hyper-targeted therapies with incredible precision, potentially discovering cures for illnesses like Alzheimer's or cancer in a tiny fraction of the time it takes us today. In logistics and finance, they could tackle these enormous optimization problems. Imagine finding the absolute most efficient route for every single package in the global shipping network all at the same time. Or analyzing every possible financial market fluctuation to create more stable economic models. These are problems with a nearly infinite number of options that quantum computers could just navigate. They could completely revolutionize our understanding of climate change. Instead of the broad models we have now, we could run simulations of our entire planet's weather systems right down to the level of individual clouds. That would give us far more accurate predictions and hopefully help us find much better solutions. And they could let us design entirely new materials from the atom up. Imagine creating things that sound like science fiction, like room temperature superconductors that could lead to lossless power grids, or vastly more efficient solar panels. You know, when you pull back and look at the big picture, you start to see that this isn't just about solving individual problems. The true impact here is a fundamental shift in how we approach problem solving itself. I came across this line that I think just perfectly captures the bigger picture here. It says that quantum computing is a fundamentally new way of thinking about information. We're not just building a better calculator. We're developing a whole new language to describe reality and to understand the universe on its most fundamental level. And that leaves us with maybe the most exciting and most important question of all. As this technology matures and we actually gain the ability to solve problems that were once considered truly impossible, which one should we point it at first? The choice we make will absolutely define our future.